We mentioned last time that even though quantities like dW and dQ are inexact differentials, we said that the entropy, which is dQ over T, is not an inexact differential. Entropy is a function which is characteristic of each macro state of the system. It's what we call a state function. So we can talk about the entropy in two particular states if we wish. So we can write entropy as SF minus SI equals the integral of ds from some initial state to some final state. And I can write that as integral from I to F dq over t. This again is a quasi-static process. What is going on then is we can assume that the system is brought from an initial state through a whole series of adjacent equilibrium states until it reaches its final state. You can have however many states in between, but it's happening such that the system is never far from equilibrium, or it's in some adjacent equilibrium state. What that means then is that the path of this integral is independent. I should say that the value of the integral is independent of the path. In other words, how we go from state I to state F doesn't matter. I can take any path I like, I'm going to get the same answer. That's why we say that entropy is a state function. The integral is independent of path and only depends upon the endpoints. That being the case, entropy is what we call a state function. And the factor 1 over t is what we call an integrating factor. It turns an inexact differential into an exact differential. Let's talk about the implications of our statistical definition of entropy. First of all, we, of course, have been using the expression entropy is Boltzmann's constant times the log of omega. So if the energy and external parameters of a system are well known, the number of accessible states, omega, should be completely determined. Therefore, I should be able to determine the entropy. It should have a unique value based on the microscopic knowledge I have of the system. Let's talk about the limiting value, or the limiting behavior of entropy. Let's move over into the quantum world. So in quantum mechanics, there's a limiting low energy that we call the ground state. Ground state energy is the lowest possible energy of the system, and it's not equal to 0. At this energy, the expectation is, though, that there's only one accessible state for the system to be in, generally speaking. Sometimes if you have a degenerate system, you might have a few accessible states, all with the same energy. But and that ground state energy will designate E naught. As E departs from E naught, though, we're going to find that omega increases very rapidly. As we said, omega is a very rapidly increasing function of E. In fact, it's going to go something like omega is going to be proportional to the difference in energy from the ground state to the power of the number of degrees of freedom of the system. But as energy decreases, the log of omega is proportional to F times K, Boltzmann's constant, which is pretty small compared to F times K at high energies. So furthermore, as E approaches E naught, the entropy then should approach 0 statistically. Now we can examine this limiting behavior in this way. So as E decreases to E naught, beta increases and becomes very large. The temperature then decreases since beta is increasing, and the entropy should approach 0. We can make the following general statement about this. As the temperature approaches some limiting low temperature, the entropy approaches some limiting low value of entropy such that S0 is equal to K log omega S. We use the term omega S to reflect spin orientations. So we expect that this is a constant depending on the particular nuclei in question, but independent of all the other parameters that you might consider. This is a function then of what we call one of the expressions of the third law of thermodynamics. That is to say, as the temperature approaches absolute 0, the entropy approaches some constant, some minimum entropy S0, and sometimes we can define that as 0, depending on the system. Moreover, this is going to be a constant independent of all the parameters of the system. Let's summarize. Statistically, we've gone through a whole lot in this chapter. S is K log omega. This allows us to relate thermodynamic laws in the terms of entropy to statistical laws. Probability is proportional to the number of accessible states, which then is proportional by this to E to the S over K. When I want to do statistical calculations, of thermodynamic quantities, some of them, what do I want to remember? First of all, beta, 1 over kt, is equal to d log omega dE. My generalized force, x sub alpha, is equal to 1 over beta times the derivative of log omega with respect to my external parameter, x sub alpha. In particular, if x sub alpha is the volume, I can say that my mean pressure is equal to 1 over beta times d log omega dV. These equations allow one to calculate an equation of state for a system, such as the ideal gas law. For example, we've shown that I can write omega for an ideal gas as being proportional to volume to the nth power times some function of energy, independent of volume, but a function of the energy of the gas. If I take log omega, I can say log omega is going to be equal to n log v plus log of chi of v plus some constant of proportionality. That being the case, if I want to find the pressure, I can write that as 1 over beta d log omega dV, which is just going to be n over beta times V, or nkt over V, which of course is the ideal gas law. So this is a very quick and easy way, and we'll do this in other ensembles as well, of computing an ideal gas law from purely statistical means. Let's compare this to the way you probably learned the ideal gas law, which is combining things like Boyle's law, Charles' law, Gay-Lussac's law into one, and doing it all empirically. As you can see, you can derive the ideal gas law without ever doing a single experiment, just using statistical means. So it's kind of a fascinating way of arriving at some basic laws of physics and chemistry. Question may occur to you that you might have a problem with the second law of thermodynamics in that, how do we know it's always true? How do we know that entropy always increases? After all, it's a function of probability. So that just says that while the probability is very, very small that certain events will happen, doesn't mean they can never happen. For decades and decades, people were concerned about whether they could find a way to defy the second law. And there was one situation that was a candidate to defy the second law, and that was a black hole. So there seems to be a very intriguing connection between entropy and black holes. The idea being that in the minds of those from probably 30 or 40 years ago, the black hole might be a situation where entropy actually decreases. The thinking was that if some system crossed the event horizon of a black hole and went inside, the entropy of the system would decrease. Well, a student of John Wheeler's named Jacob Bekenstein hypothesized that as black holes consume more material, their surface area increases as they eat more and more and more things that fall in there, increasing the area of the event horizon. Stephen Hawking reasoned that as the area of the event horizon increased, the entropy of the black hole should also increase. So area increases, and the entropy of the black hole should also increase. Well, if black holes have an entropy, the question becomes, could they possibly have a temperature? And if they have a temperature, could they radiate? And in fact, what this led to was this notion of Hawking radiation. And the example that they give is kind of an interesting one. Suppose I have pair production taking place, where I have photons colliding and causing a pair, maybe a proton, an electron and a positron forming. And let's say one falls into the black hole, and then one escapes. So it's near the event horizon. One of them falls in, one escapes. The one that escapes is radiating into space and is thus radiation from a black hole, or what we call Hawking radiation. Now, that may be that the temperature of the black hole is a billionth of a trillionth of a Kelvin, but still, the radiation occurs, entropy still increases, and so the second law still prevails. So even in situations as extreme as a black hole, we believe that the second law of thermodynamics continues to prosper. We'll continue next time with some more interesting consequences of statistical thermodynamics. In fact, I guarantee you there's one that I'm sure you never expected to hear about. Thank you.